Simple salts mean it will have one cation and one anion. That is, one acid radical and one basic radical will be present. The whole coordination compound is called as the coordination entity. There will be a central metal atom, there will be ligands, and there will be counter ions. The ions or molecules bonded to the central metal atom in a coordination entity is called as ligands. Through what bonds the central metal atom and the ligands are bounding? Yes, that is called as the coordinate bond, right? And whatever is present inside this sphere, it is called as the coordination sphere. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with a new chapter, that is coordination compounds, which is chapter 5 of your syllabus. So in today's session, we are going to see the classification of inorganic salts, right, and the differences between double salt and a complex salt, and the definition of terms related to coordination compounds. Okay, so this is a new branch of chemistry that you are going to study, that is under coordination chemistry. The chapter name is coordination compounds, right? So what exactly are these coordination compounds? So from the name itself, you can say it's something which is complex, right? Okay, it can be also called as complex salts or else coordination compounds, right? So why exactly are we studying about this coordination compounds? Do they have any applications in our day-to-day life? Yes, the chlorophyll, which you are very familiar with, which is very important for the plants to prepare their food, which is chlorophyll, a green color pigment, right? Yes, so that is very important, which is actually a coordination compound of magnesium, right? And then you have vitamin B12. Vitamin B12, which is also a very important vitamin, which is also a coordination compound of cobalt. Okay, it is a coordination compound of cobalt. As I told, chlorophyll. Chlorophyll is a coordination compound of magnesium, right? And in cancer treatment, we use a compound which is called as cisplatin. It is called as cisplatin. Even this is a coordination compound. Okay, so all these are very important in our day-to-day life. Hence, it is of course important to study about coordination compounds. So as it is a new topic for you, we are going to start with the basics of it. That is the different terms which you have to know before going on into the details of coordination compounds, right? So we'll start with the basics. Each term we will be discussing. Then we'll move on to different theories related to coordination compounds. Okay, so let us begin with the classification of inorganic salts. So as I told you, coordination compounds are also called as complex salts. So to understand about that, we will study about the different types of salts. Okay, so the first one is simple salts. So simple salts, the qualitative analysis of it, which you have already done in your lab practicals, right? So for example, ammonium bromide, ammonium chloride, all these are simple salts. Okay, so simple salts mean it will have one cation and one anion. That is, one acid radical and one basic radical will be present, right? The next one is double salts. Okay, so in the titration you have studied about more salt, that is FAS. Right, so in that, what was a double salt? Yes, it is made up of two simple salts. Okay, so it is made up of two simple salts, hence it becomes a double salt. Now what is coordination compound or complex salts? Okay, so that we are going to study in detail in this chapter. So inorganic salts are classified into simple salts, double salts, and coordination compounds, or else also called as complex salts. Now simple salts, these contain one acid radical and one basic radical. That is, one cation and one anion. You are already familiar with the simple salts in your practicals, right? Yes, zinc sulfate is an example. Zinc is the cation there and sulfate is the anion there, right? Now double salts is a mixture of two simple salts. So one example is carnallite, another one is more salt. So more salt or FAS, we have done the titration in our lab practicals, right? Yes. Moving on to coordination compounds, or else also called as complex salts, are the compounds in which the central metal atom is linked to a number of ions or neutral molecules by coordinate bonds, that is, by donation of lone pair of electrons by these ions or neutral molecules to the central metal atom. So in coordination compounds in general, we can say that there will be a central metal atom. Okay, in the center there will be a central metal atom and surrounding it will be ions or neutral molecules, and the central metal atom and this ions or neutral molecules are bound together by coordinate bond. Okay, what type of bond is present? It is coordinate bond. That is why it is called as coordination compounds, right? Okay, and the speciality of this ions or neutral molecules which is present around it is that those ions or neutral molecules will be the ones who will be donating electrons to the central metal atom. Okay, so the central metal atom is not taking part in giving away any electrons. The ions or neutral molecules present around is the one which is having the lone pairs and which will donate the electrons. So K for FeCN6. Okay, K for FeCN6. So how to name this compound we are going to study in detail in the upcoming sessions. Okay, IUPAC nomenclature of coordination compounds. As of now you can see here, this is the central metal atom. There will be a central metal atom which is the iron. Surrounding it there will be, as I told you, ions will be there. So here Cn minus ions are there which will be surrounding it. Hence Cn minus will be the one which will be donating electrons and iron will be accepting the electrons. So I hope it is clear. Now we are going to see the difference between double salt and a complex salt. So double salt is stable only in solid state but dissociate into simple ions completely in solution state. So in solid state it is, yes, it is stable, but once it is converted into solution state, what happens? It will dissociate into its constitutive ions, right? Okay, so the example you can see carnallite. What will happen? Another example is more salt. All of this will dissociate completely into its ions. So that means that in the solution phase, all these ions, iron, the Fe, ions will be separated, sulfate ions will be separated. So each of the ions will be separated in the solution phase. Moving on to complex salt, it is stable both in solid and solution state and does not dissociate completely in solution state. So it does not completely dissociate. For example, if you are taking K4FeCN6, the same example we are taking. So what happens in this case is that when it comes into solution phase, this part will dissociate into -4 and this will have a +4 charge. So the potassium will be separated and FeCN6 will be separated. Okay, so we can't get iron and Cn minus ions separately. It won't dissociate. Okay, so whatever is present inside the square bracket will remain as it is. So complete dissociation of all the ions is not possible in a complex salt or coordination compound. So as you can see here, do not dissociate into Fe2 plus and Cn minus ions. So you will get FeCN6 4 minus and 4 moles of K plus ions. Okay, so Fe plus and Cl minus which is present inside the square bracket, you won't be able to dissociate it. So I hope it is clear. Now moving on to the definition of terms related to coordination compounds. As I told you, as it is a completely new topic, we are going to start with the basic terms. Okay, then we'll move on to the details of it. So the first one, as discussed already, in coordination compound there will be a central metal atom, right? So the example we have taken is CONH3 thrice Cl3. Okay, so as you can see here, this is the central metal atom, right? So this is the central metal atom. Yes, you can see here, and surrounding it will be ions or neutral molecules. We have already discussed, right? So there are 3 NH3 molecules, there are 3 Cl atoms present here. So all of these ions and molecules are present around the central metal atom and they are called as ligands. The name for those ions or neutral molecules present around the central metal atom is called as ligands, right? Okay, now this is called as a complex ion. The whole of this is called as a complex ion and the coordination compound, right? Okay, so now for certain coordination compounds there will be a charge also present. So that is a charge of the complex ion, and through what bonds the central metal atom and the ligands are bounding? Yes, that is called as the coordinate bond, right? And whatever is present inside the sphere, it is called as the coordination sphere. Okay, so we are mentioning it in the square bracket and this whole representation is called as the coordination sphere. Okay, and we have already discussed an example before, K4FeCN6, right? So in this example, as you can see here, this is the central metal atom, iron, right? And Cn minus, 6 Cn minus will be surrounding the iron atom. That is a central metal atom. So this is called as the ligand, right? So Cn minus are the ligands. Now what about this potassium which is present outside the coordination sphere? So only this much part is called as the coordination sphere. Whatever is present inside the square bracket is called as coordination sphere. Now this is not a part of coordination sphere, but this whole thing is called as the coordination compound. Okay, so this is coordination sphere, the whole thing is called as the coordination compound. Now what do we call for this particular ion which is present outside the coordination sphere? That is called as the counter ion. Okay, whatever is present outside the coordination sphere is called as the counter ion. So I hope it is clear. Now let's move on to the details of each of these terms we have discussed now. The first one is coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules through coordinate covalent bonds. So the whole coordination compound is called as the coordination entity. There will be a central metal atom, there will be ligands, and there will be counter ions. All of this together is called as a coordination entity. Moving on to the next one, central atom or ion. We have already discussed the metal atom or ion in a coordination entity to which a fixed number of ions or molecules, that is ligands, are bound in a definite geometrical arrangement around it is called as a central metal atom. Now, it is a Lewis acid. Now, we have already studied this in class level. What is Lewis acid? So, Lewis acids are those substances which are ready to accept electrons, right? So, in the beginning of the chapter itself, I have told you, the central metal atom do not take part in donating the electrons. The ligands will donate the electrons. They will have the lone pairs and they will donate the electrons, and the central metal atom will be accepting those electrons. So, electron acceptors are Lewis acids. So, this is an important point. The central metal atom is a Lewis acid because it accepts electrons. Okay. So, example, nickel 2 plus in NiCl2 H2O 4 times and Fe3 plus in FeCN6 3 minus. So, here nickel is the central metal atom and here iron is the central metal atom. So, how exactly we are calculating the charge, that is Ni2 plus Fe3 plus, we are going to study in detail in the upcoming sessions. Okay. Now, moving on to ligands. So, we already know what are ligands, right? The ions or molecules bonded to the central metal atom in a coordination entity is called as ligands. So, whichever ions or molecules are surrounding the central metal atom, they are called as ligands. Now, already we have discussed that ligands are ready to donate electrons. So, ligands will be Lewis bases, right? Why they are Lewis bases? Because they are ready to donate electrons, right? So, in NiCN4 2 minus, yes, this will be the ligand. Cn minus ion will be the ligand. Yes, there are 4 ligands which is present. So, I hope it is clear. Moving on to the next one, that is different types of ligand. There are different types of ligands also that we have to study. There are unidentate ligands, bidentate or didentate ligands, and there are polydentate ligands also. So, let's see unidentate ligand. So, it is a ligand which has one donor atom, that is the ligand bound to a metal ion through a single donor atom. So, as we have discussed, the central metal atom and the surrounding ligand will form a coordinate bond with each other. So, unidentate ligand is present means it will bound or it will form a coordinate bond with the central metal atom through one single donor atom. Okay, even though it is a molecule, for example, H2O, if we are considering, it is having hydrogen atom as well as oxygen atom, right? But it will form the bond with the central atom. It will form the bond with the central atom only through oxygen atom. So, this is called as a unidentate ligand. Okay. So, example is H2O, NH3, etc. So, unidentate neutral ligands. So, all of these are neutral ligands. As you can see, in H2O, oxygen is having the lone pair. 2 lone pairs it is having. So, oxygen will be the one which is forming bond with the central metal atom. In NH3, you can see nitrogen will be the one which is forming the bond with the central metal atom. So, in all these examples you can see here, it is one single atom in that molecule which forms the bond with the central metal atom. Hence, it is called as unidentate ligand. Now, moving on to unidentate negative ion ligand. So, these are negatively charged. Okay. So, in this case, OH minus, again oxygen will be the one which is forming the bond. Right. Now, F minus, Cl minus, Br minus, all the halogens, Cn minus, NH2 minus, NO3 minus, all these are examples of, yes, negative ligands. Now unidentate positive ligands, NO plus and NO2 plus. So I hope what is unidentate ligand is clear for you. Moving on to didentate or bidentate ligands. So it is a ligand which have two donor atoms. So there are possibility of two donor atoms here. So in unidentate, as I have already mentioned, even though there are two or more atoms, only one atom will take part in the bond formation. Here there are two donor atoms. So one example is COO minus, COO minus. That is oxalato, that is the IUPAC name. So this we will be discussing in the upcoming session. So in this case, as you can see, both of this oxygen, in one COO minus this oxygen and one COO minus this oxygen, both of them are having the lone pairs. So both of them have the ability to bound or form a bond with the central metal atom. So there are two donor atoms here. Now ethylene diamine or ethylene 1,2-diamine, it is CH2NH2 and CH2NH2. Here also this nitrogen is also having lone pair, this nitrogen is also having lone pair. So it is having two donor atoms. So such molecules are called as, or such ligands are called as didentate or bidentate ligands. Now the last one is polydentate ligand. When several donor atoms are present in a single ligand, the ligand is said to be polydentate. Now ethylene diamine tetraacetate ion, that is EDTA, and the charge on this is 4 minus. Ethylene diamine tetraacetate ion, so is an important hexadentate ligand. So what does that mean? It is a polydentate, exactly to be specific, hexadentate ligand. It is having 6 donor atoms. Okay, so it can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. So EDTA will be having 2 nitrogen and 4 oxygen atoms through which it can form the bond with the central metal atom. Hence, total 2 nitrogen and 4 oxygen means 6 donor atoms, right? Yes. So, I hope it is clear. Now, there is another type which is called as ambidentate ligand also. So, this you can see only in special type of molecules. So, the ligands which can ligand through 2 different atoms. Okay, 2 different atoms is called as ambidentate ligand. For example, let us take the example of NO2 minus. So in NO2 minus, the nitrogen can also act as a donor as well as the oxygen can also act as a donor. Okay, so as you can see here, this is your central metal atom. NO2, okay, it is forming a bond with the central metal atom through the nitrogen atom. So this nitrogen atom and the metal ion is forming a bond here. Okay, so then it is called as nitrito-N. Nitrito-N stands for understanding that the metal ion is forming a bond with the nitrogen atom of NO2 minus. Now another possibility is ONO. As you can see here, the metal atom can form a bond with the oxygen atom of NO2 minus. Then it will be called nitrito-O. This O stands for understanding that it is forming a bond with the oxygen atom of NO2 minus. So in NO2 minus, 2 possibilities are there. Either it can form bond with the nitrogen atom or the oxygen atom. So such ligands are called as ambidentate ligands. Okay. Now moving on to the next one, SCN minus. This is also an important example. So either the metal can form a bond with the sulfur or it can form a bond with the nitrogen of SCN minus. So it can be SCN or NCS. Okay, if it is S with the sulfur, it is forming the bond, it is thiocyanate. If with the nitrogen, it is called isothiocyanate. So I hope it is clear. So this is called as ambidentate ligands. Now moving on to the next one, that is chelate ligand. When a di or polydentate ligand uses its 2 or more donor atoms to bind a single metal ion, it is said to be chelate ligand. Such complexes are called as chelate complexes. So we have already studied about didentate or bidentate or polydentate ligands in which more than one donor atom will be there. So using all these donor atoms, if it is binding to the central metal atom and forming a complex, it is called as a chelate complex. So for example, this is a didentate ligand which I have already studied, which is ethylene diamine, right? CH2NH2, CH2NH2. And here also another molecule of ethylene diamine is here. This is another molecule of ethylene diamine, and using both the donor atoms, the 2 donor atoms of one ethylene diamine and the 2 donor atoms of another ethylene diamine, it is forming a bond with the central metal atom. So such complexes are called as, yes, chelate complexes. Now moving on to the next important part, that is coordination number. Now what is coordination number? The coordination number of central metal atom or ion is the number of ligand donor atoms to which the metal is directly bound. In case of monodentate ligands, coordination number will be equal to number of ligands. So how can you determine coordination number, or what is coordination number? So we have already discussed there is a central metal atom, and surrounding it there will be different ions or neutral molecules that are called as ligands, right? So how many of those ligands are present? That is called as the coordination number. But if it is a unidentate ligand, the number of ligands and the coordination number will be equal. But if it is didentate, the number of ligands into 2 we have to do, because there are 2 donor atoms. And for polydentate, according to the denticity of that, we have to multiply it. So we will be discussing in detail about how to calculate coordination number, as well as there is another number which is important called as oxidation number, which will be discussed in the next session, right? So as of now, if the coordination number is 2, coordination number is 2 means there are 2 ligands, right? Okay, so this will be linear. Okay, the geometry will be linear. As you can see here, AgNH3 twice, AuCl2 minus. So in this case, can you tell me which one is the ligand? NH3 is the ligand here, right? So we have already studied NH3 is a unidentate ligand. So in a unidentate ligand, the number of ligands and coordination number will be same. So as you can see, it is NH3 twice, right? So that means there are 2 ligands. So the coordination number is 2. So here also the coordination number is 2, because Cl minus is also a unidentate ligand. Now if it is 4, the coordination number is 4. The coordination geometry is square planar. Another possibility is tetrahedral. So how to identify this also we are going to study in detail. So square planar complex, an example is PDNH3 4 2 plus. So here also you can see ammonia is a unidentate ligand. So that is the number of ligands is the coordination number. So it is 4. Here also PTCl4. The number of ligands is 4. So the coordination number is also 4. Now moving on to this one. Here also zinc NH3 4 times 2 plus and CuCl4. So in both these cases the coordination number and the number of ligands is equal. Now moving on to the last one, if the coordination number is 6, it is the geometry is octahedral. So in this case also NH3 as well as Cl minus, both of them are unidentate ligands. So it will be 6 and 6 here. Okay, so in the next session, in detail about the coordination sphere, oxidation number and coordination number we are going to discuss. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.